Hi students, here I am discussing about predissociation. This is a spectrum of a rotational fine structure of an electronic vibrational transition. In this structure you can clearly see the rotational fine structure and vibrational core structure. Vibrational core structure 0, 60, 70, 80, 90, 10, 11, 0. Okay. This spectrum you can clearly see the rotational fine structure. These are the rotational fine structure. This is the vibrational core structure. Okay. Here this region is marked as region of predissociation. That means here the rotational fine structure is not clear. The rotational fine structure become blurred and lost in these regions, or otherwise known as a continuum is appear in this region instead of a discrete energy level. A separate energy level, a continuum is appear in this region. This region is known as predissociation. Okay. So, why does a continuum is appear in the spectrum? Above the dissociation limit, the energy is not quantized. And energy continuum appears instead of a discrete energy level. That means normally a continuum represents a dissociation of the molecule. After the dissociation, molecule will not exist, and so there is not quantized energy is there. As a result, instead of a discrete energy level, you can see only a continuum. In the spectrum of a rotational fine structure of a vibrational electronic transition, a continuum normally appears at the end of the spectrum. Sometimes a continuum may appear before the true dissociation limit is known as predissociation. That means as a result of dissociation of the molecule, normally we expect a continuum at the end. Okay, this continuum may be due to the dissociation, but sometimes this type of continuum may appear before the actual space. That is known as predissociation. Why is it so? Predissociation can be usually explained as a result of internal conversion from an excited state A into a dissociated state B. That means in this energy diagram, this is a potential energy diagram of a representation of a ground state molecule and an excited state molecule. This potential energy diagram, you can see a minimum potential energy curve. This represents the stability of the molecule. So in this first diagram, both the ground state and excited state molecule potential energy curve has a minimum. That means both the ground state and excited state is stable. But here the ground state energy diagram has a minimum, is stable, but in the excited state you can see the different curve A and curve B. Curve A has a potential curve A potential energy diagram has a minimum, that means it is stable. But the other curve, the curve B, represents a continuous curve that has a minimum in the energy curve. That means it is unstable. So when a molecule is molecular transition occur from electronic transition occur from this state to excited state, that means a stable energy state. Sometimes this from here molecule may cross over to the curve B. That means a stable state. A molecule may transfer a stable curve to an unstable curve B. That means then it will lead to dissociate. In the excited state, sometimes a molecule may cross over to the continuous curve B from a stable state, hence dissociation of the molecule will occur. This is a radiationless transfer and faster than the time taken to rotate, but usually slower than the vibrational time. Thus, predissociation will occur before the molecule rotates, and hence rotational fine structure will be destroyed in the spectrum. If the crossover is faster than the vibrational time, then a complete continuum will occur in the spectrum. In the spectrum, the vibrational core structure and both the vibrational core structure and rotational core structures are blurred. That means that crossover is very faster than vibrational changes and rotational changes. Okay. As a result, both the rotational fine structure and vibrational core structures are blurred this region. Okay. Thank you.